In this video, I give a brief introduction into the symbolic toolbox of Matlab. So please open example symbolic functions. Let me step through the script. So you see we start in line 1 with a clear command window, then we clear the workspace. Now let's start with symbolic constants. If you square the square root of 2, I mean the numerical value of square root of 2, and then subtract 2, you will not get 0 because of rounding errors. In fact, you get something in the order of 10 to the minus 16. If you want to compute without rounding errors, you can use symbolic constants. This is capital S2 is the symbolic value of square root of 2. And if you now square S2 and subtract 2, you get 0. Let's have a look at the class of S2. So wrong window. Let's type whose S2. And you see that S2 is of class sym, so it's a symbolic constant. We can also define symbolic variables in this way. Syms and then the names. In order to distinguish symbolic variables from ordinary variables, I use capital letters for symbolic variables in this script. So let's define two symbolic variables, x and y, and you will see they're also of class sym. So they are symbolic variables. I can now use these symbolic variables to define symbolic functions. So this is our first symbolic function, and I define it like this. It's called f. It has one argument, which is the symbolic variable capital X, and then this string defines the computation that is to be done with the symbolic variable x. So this is a function of a single real argument, and the class of f is now symfun, so it's a symbolic function. You can convert symbolic functions to either inline functions or to an ordinary Matlab function. And I will show you why you want to do this in a minute. So let's compute to an inline function. This is done by the function, the Matlab function fcncheck. So this takes the character string of f and converts it to an inline function. And here I give the argument vectorized. So you see that all the multiplications and the divisions are done pointwise. So I can use a vector argument for this inline function. I can also convert the symbolic function f to an ordinary Matlab function by this function, which is called Matlab function. Note the capital F. And it returns a handle to this function. So this is a function handle, and you see it's also a vectorized function. This is default in this case. Now, how do we evaluate a symbolic function? Well, like any other function, I give the arguments in brackets, and what I get back is a symbolic expression. If I now type who is ans, it's again symbolic. So the result of this evaluation is not a numerical value, but a symbolical variable. We can, of course, convert this to a numerical value by using the function double. So let's do this. And now I have the value 1 over pi, which is about 0.3183. Now, let's try to evaluate a large vector with the symbolic function f. And you will see that this is rather slow compared to the inline or the function handle. So let me define a vector of length 10,000. And now evaluate this vector with the symbolic function f, and then I convert to double. So let's see how long this takes. This takes about 2.5 seconds, which is pretty slow for a vector of size 10,000. Now let's compare it with the inline function and the function handle. With the inline function, it takes 4 milliseconds, and with the function handle, it takes 1.5 milliseconds. So it's much, much faster, about a factor of 1,000. So if you want to evaluate a symbolic function on the large number of points on a large vector or matrix, then you better convert it to a function handle and then evaluate it. Now let's do some symbolic operations on this symbolic function. For instance, we can compute the first derivative with respect to x with the function diff. So diff takes the symbolic function as a first argument and the variable as a second argument. If there is only one variable, as in this case, you might also drop the second argument. I can show you in a second. So this is a first derivative, and I can do the same by simply writing diff of x, capital X. No, not diff x, but diff f. Okay, so now it's correct. I can either type diff f or diff f comma x. If there is only one variable, it's clear that the derivative is with respect to capital X. I can put a third argument and compute the second derivative. So this is a second derivative of the symbolic function f. I can try to compute an indefinite integral. You can guess what the result is. Yeah, it's the arctangent function of x divided by pi. And I can compute the definite integral of this function from minus infinity to plus infinity. And I get the value 1. This is still a symbolic one, as you can see here. If I type who si, this is a symbolic constant or symbolic variable I with a value 1. Of course, I can convert this to a numerical result again by using double. Okay, now let's look at a somewhat more complex example. I define a third order function of two variables, which in addition has 4 parameters, symbolic parameters, which I call A, B, C, D. So this is a function definition. So I say g of x and y is this string, this symbolic expression, which contains both x and y and the symbolic variables a, b, c, d. So let's have a look at the function g. So this is symbolic function. I can again take derivatives. Now I have to specify which partial derivatives I want. So this is the partial derivative with respect to capital X and to y. So now I have the gradient of this function. I can differentiate again and I get the second order partial derivatives. Of course, gxy and gyx have to be identical. And I can store these partial derivatives in the Hesse matrix, the matrix of second order partial derivatives. So this is now the Hesse matrix, the general expression of the Hesse matrix of this function. Now let's choose some particular values for the constants a, b, c, d. And this I can do by the function subs, which stands for substitute. So now I take g, I substitute these numbers for these symbolic constants. So this is a cell array of symbolic names, and this is a cell array of real values. So this will substitute a with 1, b with -1, and so on. And I can do this for g, for the gradient, and for the Hesse matrix. So, after having done this, I have now the Hesse matrix for this particular choice of the values a, b, c, d. H is still a symbolic function, but I can do some simple operations on this. For instance, I can take the inverse. So the inverse function knows how to deal with a symbolic function. So let's try to invert the Hesse matrix. Okay, this is very simple. It's diagonal, so you see just the reciprocal values in the diagonal. And if I ask for the class of h_inf, it's still a symbolic function. Now suppose we want to find the stationary points of this function, which means the zeros of the gradient. This is done by the function solve. So this looks for zeros of these two functions with respect to these two variables, and the results are stored in the output x0 and y0. So these are the x and the y coordinates of the stationary points. Okay, there are 4 of them. So if I compute the length of x0, for instance, I get np, the number of stationary points. And now I can compute the Hesse matrix at the stationary points. If you want to know the type of the stationary point, you have just to do just that. The Hesse matrix at this point will tell you whether you have a minimum or a maximum or a saddle point. I will leave the details for the assignment. So let's loop through these stationary points. So this is the first one. This is the symbolic function of the Hesse matrix, and this converts this result to a numerical matrix. So this is the Hesse matrix at the first stationary point, at the second, at the third, and at the fourth. So you see the 4 Hesse matrices are all different, and I leave it up to you to figure out what the type of the corresponding stationary points are. I remind you, if all eigenvalues are positive, you have a minimum. If all eigenvalues are negative, you have a maximum. If you have eigenvalues of both signs, then you have a saddle point.